something about the assumptions. So my theorem, still unpublished, since I don't open, is let phi from the strictly positive orthan into non-negative orthan, prices into commodity bundles, be a C1 demand function induced by a strictly quasi-concave utility function U which we assume to be of class C2 on the strictly positive orthan. N satisfies its first order partial derivatives are strictly positive on R plus plus N union phi of R plus plus N. These are the assumptions. I will make comments about the assumptions later. Then the result is phi is monotone if and only if, I mean, you remember Mityushin-Polterovitch's sufficient condition. There was that expression smaller than 4. So here I get minus that expression to be less than or equal to 4, but this is not the end of the story. 4 minus x transpose gradient of u of x divided by gradient of u of x transpose Hessian of u of x inverse gradient of u of x for every x in the strictly positive orthan such that the Hessian of the utility function is non-singular. This is not the end of the story yet. I'm saying what happens at points where the Hessian is non-singular, and what has to happen at points where the Hessian is singular. This expression is less than or equal to 4. I mean, simply Millerand, but with non-strict inequality for every x. Such that the Hessian is singular. Or I have to distinguish singular or not, because the first condition only makes sense if the Hessian is non-singular, because I'm taking the inverse matrix. Okay? Well, this is the result I got. In which way? As I told you, I found a clear proof of Mityushin-Polterovich theorem in an appendix of the book by Hildenbrand. And then I thought, can it be improved? And then it was not very difficult to refine that proof. And then I obtained this new result. The proof I have at home at some handwritten notes, which I hope I have not lost them. And someday it will be published, and together with other things, in a joint paper with John Kua, who has probably already forgotten that we had that project. This is why he is not reminding me. And but let's make some comments about this result and how it compares with Mityushin-Polterovich. I cannot avoid differentiability. Of course, how could avoid it if I am refining a proof in which differentiability is crucial? But look, in Mityushin-Polterovich, the utility function was assumed to be concave, which is meaningless from an economic point of view. And here I am assuming just a strict quasi-concavity. This is not weaker than in Mityushin-Polterovich, because he is not assuming a strict strict concavity, just concavity. But I think the price is worth to pay by moving from concavity to quasi-concavity to impose strictness, because strict quasi-concavity is a property of preferences, unlike concavity. So I'm very happy to do it under this better assumption. There is another little technical issue in which Mityushin-Polterovich are, let's say, better than me in that they assume positivity of the partial derivatives on the positive orthant. But I have to go a little bit beyond. I need to consider also points which may be in the boundary if they are in the demand, in the range of the demand function. Okay, if it happens that some phi of p is not in r plus plus n, but then it's in f plus f of, that phi of p is in r plus n, then I need to assume that the function is situated around that point. I mean, it's defined on a neighborhood of that point, and then its partial derivative is also positive there. But this is, in my opinion, a very minor detail. So I think these assumptions are quite acceptable. In particular, if you accept it, using Polterovich, then you should accept much more happily this one as the replacement of concavity with strict quasi-concavity is a significant improvement. But the main contribution is not that refinement, but is that now we have if and only if. This is a necessary and sufficient condition for monotonicity of demand. I have never seen any other in the literature. I think one cannot find. Okay? And what about this condition? First of all, nothing to comment in the second part. It's just Medjushkin Polterovich with less than or equal to. But I observed that we don't have a clear interpretation. We did our best, and we found some mathematical equivalent statements which didn't shed much light on the economic nature of this condition. So nothing else to comment on this part. On that part, first of all, I am assuming that the Hessian is non-singular, but in spite of being non-singular, it might happen that this is the denominator vanishes, but it doesn't. Okay? It can be proved because of the quasi-concavity property of the Hessian matrix. More than that, assume for a moment that U is concave, that as in Medjushkin Polterovich. Then the Hessian is positive definite, negative definite, if non-singular. Then the inverse is negative definite too. So this should be negative in the concave case. But in the quasi-concave case, it need not be negative definite, but the Hessian matrix of a quasi-concave function has also some nice properties. There are second-order characterizations that we didn't discuss for quasi-convex functions in terms of the Hessian. Using that properties, it can be seen that in spite of this matrix not being negative definite, this number is always negative. Okay? Not for an arbitrary vector here and there, but for the gradient of U. There is the second order conditions for a quasi-concave function establish a relation between the gradient and the Hessian of that function. And using that conditions, you can see that this is always negative. And the numerator is always positive so positive, negative, negative, this condition is weaker than that in Midyushin-Polterovich. It's weaker. The quantity is positive. No, I mean, so if Midyushin-Polterovich holds, this holds too. Because I'm adding something positive to the right-hand side. So this is weaker. And because it is weaker, it's not only sufficient as in Midyushin-Polterovich, but also necessary. Okay, so we knew that we had to weaken Midyushin-Polterovich if we wanted a necessary and sufficient condition. And this is the weakening, well, together with the second part. This expression is not the first time to appear in the literature. I forgot, but when reading my chapter in the Handbook of Generalized Convexity, Generalized Monotonicity, if somebody is interested, just ask me and I will send you an electronic copy. Then I read that I wrote there that this expression appears in the Millegón paper I mentioned that inspired me some other result. That paper, by the way, was on the uniqueness of equilibrium, of economic equilibrium. Monotonicity of demand was not the aim of that paper, was just something in the side. And what I had also forgotten, but I recalled yesterday reading my own chapter, is that Millegón observed that this expression does not depend on the particular representation U of your preferences. So if he is right, I'm sure he is, if your utility function satisfies this, any other utility function representing the same preferences would also satisfy this. So this is invariant. This depends only on preferences. Okay? This is what he said. And this is very interesting because this means we are close to get what I wanted. Close. Relatively close. Close but very far. Let's say closer. To obtain a characterization of monotonicity in terms just of properties of preferences. And something that came to my mind when looking at this, but only yesterday, I had not touched this stuff since I don't know when, even not to give talks or courses, is as follows. If without the minus term here, we analyze this and saw that this is equivalent to a certain convexity along race property of the utility function, question, can one say the same about this whole condition? This should be very interesting. I don't know if it is easy or difficult, but now I propose you this problem. You know the techniques because you see what we did when there was just 4 in the right-hand side. So, it's not working? Maybe is misplaced. Is this better now? Yes? You think so? No? Okay. I hear myself the same, so I don't know. Well, any comment about this result? Do you think there is a chance to interpret this condition in terms of some convexity along race properties? I didn't try. It may be an easy exercise, or it may be terribly difficult, or it may be even impossible. Maybe it's not equivalent to any convexity along race property. Well, now I often told you that the results, the duality results between direct and indirect utility functions I presented were not totally symmetric because I wanted to avoid technicalities, but that I had obtained such, let's say, perfect duality results. So I'm going to state, without proof, the result I obtained in a paper I published in 1991 in the Journal of Mathematical Economics. And then you will understand that it must be a little bit too technique, okay? But I think it's good that you know the result. So the theorem is and it's published in the Journal of Mathematical Economics, volume 20, (1991). For the symmetry of the result, I have to accept that both u and v take infinite values. Okay, so I accept extended real valued functions. So let v from r plus n into the extended real line with minus infinity and plus infinity. For quasi-convexity, this is not artificial, as I already mentioned. The value minus infinity is quite acceptable. In fact, when I gave you a set of suprimal generators, I used the value minus infinity. The other day I was thinking that when I will tell you that result, I forgot to give you the geometric intuition. And then you will see is for one variable functions, that it's quite clear. I mean, suppose you have a quasi-convex function, not necessarily continuous, not a real line, well, lower semi-continuous, and then the point is that suppose we are here, I fix this level, then because from that point on the function is increasing, this constant will be below. And from the other side, minus infinity will be certainly below. And this was the kind of minorance that we were using. And of course, I can approach in this way the value of the function as much as I want. That was the idea that I forgot to tell you. Okay, so let V be any function. When is it an indirect utility function? Because here, at this point, we departed from what we did in production theory. In production theory, first I said a cost function has these properties. And then I had, if this function has these properties, then it is a cost function. There is a production function that generates it. Here I never said, if V satisfies this condition, it must be an indirect, it must be a utility function. We didn't have a characterization. So, then, this is an indirect utility function. So, there is some utility function. If you feel uneasy with the assumption that this is extended real value, don't worry, I will remove it later. Okay? But for the time being, for the symmetry of the result, I can remove it, as you will see, but then we will lose symmetry. Okay? Then there exists a utility function such that V is the indirect utility function associated with U. So it's the indirect utility function for some U, if and only if, which are the properties of V? V is non-increasing, in fact we saw that an indirect utility function is always non-increasing, evenly quasi-concave, I already said some words about evenly, but maybe it will be convenient to insist now, because also if we are going to discuss maybe tomorrow about quasi-convex duality, this will again play a crucial role. Okay? Evenly quasi-convex. N satisfies evenly quasi-convex. V is an indirect utility function. N satisfies the following condition. V of P is less than or equal to the limit as alpha goes to 1 from the left of V bar alpha P Here V bar denotes the lower semi-continuous hull of V. The largest lower semi-continuous minorand of V. For every P in the boundary, which is nothing but R plus N minus the orthon, the positive orthon. Okay? This is if and only if. I have not finished the statement, but before finishing, maybe we need some comments about even quasi-convexity and about V bar and about this limit condition. So, and if you become interested in even convexity, I recommend you the book Even Convexity, which appeared a couple of years ago in Springer by my friends and colleagues from Alicante, Miguel Ángel Goberna, Marga Rodríguez, José Vicente, and María Dolores Fajardo. Excellent book. So, what is an evenly convex set? When do we say that C is evenly convex? There are several equivalent definitions. One of them. For every X bar not in C, there is X star in Rn such that X star is strictly less, or X star n, is symmetric, strictly less than X star X bar for every X in C. You can take this as the definition. And then proof. All these proofs are easy exercises. If you are interested to see some of the proofs, just ask me. They are easy. This is the same as saying that C is the intersection of a collection, of a family of open half spaces. Another equivalent definition: C is the intersection of a collection of open convex sets. Another equivalent definition, C is convex, and through every outside point, there is a hyperplane that does not intersect the set. All these properties are easily seen to be equivalent and then define even convexity. As I said, if you are interested in seeing some of the equivalencies, just ask me. It's not hard. And there are many more equivalent notions, equivalent properties to even convexity, as you can see in that excellent book. And then, which sets are evenly convex and which are not? I already mentioned, in the real line, every convex set is evenly convex. Every open set is evenly convex. Even an intersection of open sets is evenly convex. You just take one, it is evenly convex. Every, in particular, every open half space, but every closed convex set is also evenly convex. Do you agree? What's the reason? Because every closed convex set is an intersection of closed half spaces. But can you hand replace in this sentence closed with open? Yes, because every closed half space is an intersection of open half spaces. What is a closed half space? Is something defined by an inequality of this type. But this is the same as saying x star x is less than or equal, is strictly less than L for every L greater than K. So I have expressed a closed half space as an intersection of infinitely many open half spaces. Okay, so every closed convex set is evenly convex. So even convexity is less demanding than closeness and convexity. But I gave you an example, I remember, so no need to repeat it now, of a set in the plane which is convex but not evenly convex. Okay, so take the union in Rn, n greater than 1. The union of a half space with some convex set in the boundary. A convex set which is not the empty set or the whole boundary. Then in this way you get always a convex set which fails to be evenly convex. But, so convex sets that fail to be evenly convex are somehow exceptional. They cannot be open, neither open nor closed. And they have to be in dimension at least 2. Okay? Well, this is the notion of even convexity, which is very important, in particular in connection with quasi-convex duality. And then one says so when I said here intersection of a collection of open half spaces, equivalently I could have said an intersection of open or closed half spaces. I mean, you have some open and some closed. Because the closed are intersections of open, you have intersection of open, so it's evenly. Okay? Now, with this notion, we are ready to give the definition of an evenly convex function. F is evenly quasi-convex if and only if, definition, the lower level sets are all of them evenly convex. If I remove evenly here and there, I get the definition of quasi-convexity. Okay? So a function is quasi-convex if all of its lower level sets are convex. Then if all of its lower level sets are evenly convex, I call the function evenly quasi-convex. And evenly quasi-concave would be when the upper level sets are evenly convex or when minus f is evenly quasi-convex. No? That's clear. That's a very good question. In fact, I'm going to mention that. You can consider, I mean, classically, we look at convex functions, they have a convex epigraph. If the epigraph is convex and closed, then the function is convex and lower semi-continuous. And what is if the epigraph is evenly convex? This is your question. This may happen, and then you call the function evenly convex. But the class of evenly convex, I have worked on them, and you can find in the book by my friends. But it's a very, how to say, special class of functions. Well, every lower semi-continuous convex function is evenly convex. But are there evenly convex functions which are not lower semi-continuous? There are, but they are very strange in my opinion. Okay, they're not very useful for practical purposes. So you can say a lot about them, and I said something. I remember what I said. I don't remember, but I work on them. But okay, they have only a theoretical interest, but not for practical purposes. But evenly quasi-convex is different. Evenly quasi-convex is very important, in particular for duality purposes. Duality theory for quasi-convex functions simplifies a lot when you use even quasi-convexity instead of lower semi-continuous quasi-convexity. So, then you already understand this part of the statement. Then about V bar. I said V bar is the lower semi-continuous hull of V. What does it mean? The class of lower semi-continuous functions is closed under the pointwise supremum operation. So if you have a collection of lower semi-continuous function, the supremum of this collection is lower semi-continuous too. So given a function V, you can consider all its lower semi-continuous minorands. There is at least one, the constant function minus infinity. We are admitting the value minus infinity. There is at least one. And then you collect all these minorands, take the supremum, you get a lower semi-continuous function, which is a minorand of V, and by definition it is the largest. We took the supremum, the largest such minorand. So this is what we call V bar. So this is a quite technical condition because we are comparing V with V bar. V bar, of course, is below V. Okay, but instead of in spite of being below V, we still have this condition. Okay? And it can be proved that this condition is automatically satisfied on the interior, on R++ n. So for this reason, I stated it only on the boundary. But you can remove boundary because outside the boundary is satisfied automatically. Well, but I have not finished that statement. The last part of the statement is, in this case, so if V is an indirect utility function, we know that such a utility function exists, but we can take it regular. What does it mean, regular? The same as V, but changing the sign. So we can take V non-decreasing, oh sorry, U non-decreasing, evenly quasi-concave, and such that let us change signs here. So U of x is greater than or equal to the limit as alpha goes to 1 from the left of what? I have to change the sign of V. So what I get is no longer the lower semi-continuous hull, but the upper semi-continuous hull. The smallest lower semi-continuous majorand of U. What I call U bar. So U underline. So V bar is lower semi-continuous hull, and here U bar is upper semi-continuous hull. This is below the function, the largest lower semi-continuous function below the function, and this is above the function, the smallest upper semi-continuous function above the function. Again, everything makes sense because the infimum of a collection of upper semi-continuous function is upper semi-continuous. Okay? So U bar of alpha x for every x in the boundary, because on the interior it's automatically implied by the other properties. This is not yet the end of this long statement. The last part is, under these conditions, U is unique. So you may have, in general, you have infinitely many utility functions inducing the same indirect utility function, but only one with these nice properties. And this unique regular U is the largest among all. And this unique regular U is the one we know. The one of our formula, the formula we discussed. Okay? No, no, it's limit. No, it is correct. It's limit. Limit is limit, doesn't change. Another thing is that we can think about this if you want. I mean, here, limit, because V is non-increasing, then V bar is non-increasing too. It can be proved. So if it is non-increasing, I am approaching from below, P. So I am approaching, I said non-increasing, or let's say decreasing. So I am approaching with largest values. So this V bar is the infimum. So if you feel uncomfortable with 1 minus, instead of this, write here infimum, okay? And then there it will be supremum. but infimum over alpha less than 1, supremum over alpha less than 1. This doesn't change. Okay. If you change signs here, inequality reverses the order, but the limit, no. I mean, no? Because?
This one is a minor end of V bar. The minor end of V, so we will approach, like we are approaching to P from the left. But when in this case it's a major end,
Yes.
we will approach P from the right.
Perfect. And so what?
Just.
There is no contradiction. I mean, you may like it or not, but life is like this. So it's correct. I mean, when I learned about this, I remember at the beginning when I was doing quasi-convex duality, etc., I attended many presentations, including by Siegfried Scheibel, on this duality between convex and between direct and indirect utility functions, and I didn't understand the essence. Once I said, it's time to try to understand, and then I understood. And then I said, but a result of this type is missing. And then I struggled until I succeeded to get this result. But this is, I think, beautiful. Should not say it because it's my result, but in particular, it establishes a bijection between quasi-convex functions satisfying this, that, and that, and quasi-concave functions satisfying the symmetric properties. It's a bijection because you can recover the original function. Okay? This makes part of quasi-convex duality in a sense. It's a very special quasi-convex duality motivated by an economic problem. But of course, you don't need any interpretation of as utility functions or prices or goods or anything. These are functions. I told you that if you don't like to admit extended real valued utility functions, then I will try to make you feel happy. One of the results in my paper is that if U is R bar, if U is regular, by regular I mean satisfying all these properties, then U is finite valued if and only if V is bounded from below and is finite valued on the strictly positive orthon. Then, what's the conclusion? That you may say, okay, it's a nice duality theorem between direct and indirect utility functions, but I don't like that you consider extended real valued functions here. Okay, with the indirect utility function, you have to accept. It's not the primitive. But, I mean, you have your utility function as you want it, finite valued, but then you compute the indirect utility function and it goes to plus infinity sometimes. Okay, no problem. But then if you want a bijection involving only finite valued utility functions, then you have it, but you lose the symmetry. So the bijection would be between finite valued utility functions satisfying all these properties and non-increasing, evenly quasi-convex, etc. functions which are bounded from below and finite valued on the positive ortho. I'm presenting just a selection of the results I published in that paper. And then I think it's time to start. But to motivate what I will tell you tomorrow, I will want you to meditate on the following issue. So I said that V, the indirect utility function, expresses your preferences with respect to price vectors, with respect to supermarkets. You prefer a supermarket where prices are V, P, to supermarkets where prices are Q, if V of P is greater than P of Q, okay? But then suppose you have two price vectors, two supermarkets if you want, and you compute the indirect utility function, and you find it is the same. So are you indifferent? As I suggested, I mean, if this really represents your preferences with respect to supermarkets, you should say, yes, I am indifferent. So I will decide at random to which supermarket to go for shopping today. Is this correct? Always? I mean, if V of P is equal to V of Q, is really correct to deduce that you are indifferent between P and Q? Or it may not be the case. I leave this as an open question, and tomorrow I will answer this question, and then you will see in which high technicalities you get involved if you want to be more precise. After you realize that this does not necessarily mean that you are indifferent with respect to both. If you want to correct the theory or to refine the theory, you will say how messy it becomes. I did it together with a friend of mine, an economist. Okay? So this will be the first topic tomorrow. Okay, now we stop here, okay? I mean, what I mean is that V does not necessarily faithfully represent your preferences, because it may be, theoretically of course, it may be that V of P is equal to V of Q, and you say, no, I strongly prefer P to Q. This may happen. You will see tomorrow why.